talk about homotopy. It's going to be very introductory, and if you don't know anything, I hope this will give you some intuition of what's happening and why we want homotopy rather than the strong notion of homeomorphism, which is maybe something you are more familiar with. So if we have two spaces, topological spaces, if you don't know what this word means, you can just think of them as shapes. You don't need to freak out about it. So usually we need to come up with an idea of what it means for them to be the same, okay? And the first one that we learn in undergrad is homeomorphism. So we say that X and Y are homeomorphic. And this means they're the same topological space, but this is a very vague notion of what it means to be the same. If there exists a function x to y such that we require three things. One, f is a bijection, so it is 1 to 1 and on 2. 2, f is continuous. Sorry about squeeze. And the inverse is continuous. So when this happens, for topological space purposes, we treat them as the same space, and we expect them to hold same topological properties. I want to give some baby examples for some homeomorphic spaces. So, for example, examples. 1. Well, I can just write the name of the function, I guess. So the tangent function is a continuous function from this interval to the entire R. And its inverse is also continuous. So this is a homeomorphism. So this tells me, topologically speaking, this open interval, negative pi, is the same as the entire real line, right? Well, then you might think, okay, is this special to this open interval? No, because once I have this, well, you don't need to take these intermediate steps, but I think it's easier to see. So I'll try to make the open interval 0, 1 homeomorphic to this space, okay? And it's just like stretching and translating this open interval, so it should be easy to come up with the function. So let's try. So the way I think about this is the length of this interval is 1, and the length of this interval is 2 pi. So I need to stretch it first by a factor of 2 pi. Okay, now I set the length of the interval to be 2 pi, and now I want to translate it back to negative pi. So I think this should work. This is obviously a continuous function because it's a polynomial in terms of x, and its inverse is I think also continuous. So this is also a homeomorphism. Okay, then if I also write a homeomorphism from this to this, for any a and b, well, okay, let's be pedantic and say this. Okay, So the same reasoning, the length of this open interval is b minus a. So I need to scale by that. But the starting point is not 0, it should be a. So I think if I add a to it, it should work. Okay, so these three conditions tell me that every open interval and the real line, they're all homeomorphic to each other. So when it comes to topology, like if you're a topologist and if you're looking at an interval or the real line, they're the same thing. You don't see a difference. Okay? Any questions so far? Yeah.
Reel sayılardaki süreklilik ile topolojideki süreklilik farklı mı?
Okay, so he is asking whether the definition of continuity is different. Here, it's not, because this is a subspace of R, so it is the same definition. But if this space, yeah, in here, it is a little bit different, but I don't want to get into the details. But for this, for the purpose, you can just intuitively say that if, okay, the way I think about continuity is points that are close to each other are mapped to points that are close to each other, whatever that means. But if you delve into the detail, it gets a little bit technical. But yeah, it's not the same.
Okay,
Yeah.
thanks. Is it something about? I'm sorry, let me paraphrase it. Can we define continuity? I'm sorry if it's out of topic, but
No,
can we define continuity without using metric?
we can.
In a way.
We
Yeah.
can. That's if you
That's
take
the-
a course on topology, that's one of the first things you
Okay.
do. But it gets technical very quickly and it gets very abstract. So I'll try to black box that. Okay, just believe me when I say something is continuous. But I'll try to give the intuition behind it. Okay. 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 Let's try to see something that is not homeomorphic. So I claim that the circle S1 and R, or an open interval, they are not homeomorphic. Okay, there are a few arguments for this. One, if you're familiar with the concept of compactness, you might say, well, this is compact and this is not, and if they were homeomorphic, they would both be compact or not compact. So this could not happen. But there is also an argument that does not need that fancy word, and I'll try to give that argument to you if I can find the razor.
Eraser?
Sakladım. So usually showing that two spaces are not homeomorphic, what we do is, well, you need to show that there does not exist such a function, which is kind of tedious. So what we can do usually is we come up with some properties, and if they are the same space, if they are homeomorphic, they share that property. So that's what we do usually to show two things are not the same, okay? But in this case, I'll show an easier example. Look, so suppose we have an homeomorphism, S1 to R, a homeomorphism. What I'm gonna do is I'm gonna choose my favorite point in S1, P. Let's P in S1. I mean, it's not my favorite. It's any point you might like on S1. So I'm gonna restrict F to everything but P. So now this is a function from S1 minus point to R minus whatever that point is mapped to. Okay. It's not weird, right? You can understand this notation, I hope. Okay, well, if this is a homeomorphism, then this is also a homeomorphism. Because this is bijection, and it's continuous, and its inverse is also continuous. However, it is easier to see that these are not homeomorphic. Why? Because if you think about S1, and if I remove a point, like maybe I remove here, it is still a connected space. It is one piece, right? If you're an ant living on S1, if you want to go from here to here, you can go all the way around. But if you're on the real line, and if you remove a point, well, now you're disconnected. You can't go from this side to this side. So they can't be homeomorphic. Okay, any questions about this example?
Sorry, how is the connectedness sort of more mathematically encoded, I guess?
Okay, that's like you're asking the definition of being connected?
Slash, how does it manifest in like when you have like a, like how does this directly lead to a contradiction?
Okay, yeah, I'm black boxing certain things.
I think I'm curious about the same thing.
Okay.
I will try to rephrase. How do we detect disconnectedness? Maybe.
Okay, one thing, okay, maybe I can say path connected, which is easier to see.
I mean, I see it
Oh, you
visually,
want to show it mathematically?
yeah.
Yeah.
Okay, one thing is, if you have two open sets that are disjoint from each other, such that their union is your space, okay? That's called a disconnected space. Okay, okay, I'm gonna write it. So since these are, if you've seen some metric spaces, or if you have an idea of what an open set is, I'm gonna write what it means to be disconnected. So let X be a space, and we say that X is disconnected if there exist open sets that are not empty, and their intersection is empty set, and their union, I know it sounds like a lot of things, is X, that is disconnected. So in this case, this open interval union this open interval, they don't intersect, they are non-empty, and their union gives me my space. So it's disconnected. But here, you can try, well, it's not a good, it's not a proof, but you can convince yourself that you cannot cover this with two disjoint open sets.
So just really quick, would looking at pre-images be helpful for this kind of, like we should get some kind of disjointedness in our pre-image and then...
Yeah, if this was an homeomorphism, then, well, now I need to define what continues. So the pre-image should also be open, but I didn't say that, so I don't want to black box those things. Okay. But if you know the definition of continuity for topological spaces, it's easy to show that being connected is a topological invariance. If you are curious about it, we can talk about it after. Any other questions? Okay. Yes.
Okay, so some say the real line is like a circle, but there's a point at the infinity together. It's like, I guess, Alexandrov compactization.
Yeah, you can also have one-point compactification.
Yeah, after applying this, can we make this homeomorphic?
The one-point compactification of the real one is homeomorphic to the circle. Yeah, if that's what you're asking. Yeah. Okay, now I want to slightly change. I want to give you an alternative definition for homeomorphism because it will make us see what homotopy equivalence will be in a better way. Okay, I want to give you a different perspective. So we say that X and Y are homeomorphic. I hate this word. If Okay, now I'm gonna change the definition, but you can easily see that it's the same definition that we started with. There exists f. Okay, from now on, every function is continuous. Okay, unless I state otherwise. F from x to y. Okay, this looks very bad. And g from y to x, such that f composed with g is identity of y, and g composed with f is identity of x. Okay, I hope you can see that this is literally the same definition as being homeomorphic. But I want to state it in this way because homotopy equivalence is very similar. It's going to be a similar picture here, but we want to somehow weaken this equality, okay? This is too strong. We want to come up with a meaningful way to loosen this strength of being equal. So that will be the goal. Which leads us to our next definition. Okay, so here comes the fun part. Suppose we have two maps, x to y, and we say that f and g are homotopic if there exists a function h, x times I, and by I, okay, let me write it here. I is the unit interval. Such that h, so now I have two arguments here. So, okay, it's not something physical, but it helps to think of this as time, okay? So at time 0, my function h, what h does, is literally the same as f. And at time 1, it is g. So you can think of it as a movie deforming f to g, okay? So let me give you an example. Suppose this is f, the image of f, and maybe this is g. So now I need to come up with a movie that deforms f to g, okay? So this will not be very mathematical, but I also write what it is. So this will be my homotopy from f to g. Okay, so if you look at the definition, if you fix a time, it's a map from x to x. Oh wait, this didn't have to, sorry, this is y. This doesn't. So it's a map, at each time I have a function. Okay, here it looks like a path, but at each time I have a function. Also, if I fix a point and look what happens to that point through time, it also has a path. So every point also has their own movie or something. Okay, any questions about this definition? This is the key definition that will lead to everything else.
So if we were to define it like an interval mapped to the family of functions. Like,
Yes.
so at 0 you have f, at 1 you have g, and between there are different functions.
Yeah.
Yeah, yani it wouldn't be useful as this much. As
I think
this
it's the same
definition
thing.
as
This is, okay, if I understand your question correctly, this is also a family of functions. At each time, at each fixed t, I have a function from x to y.
But also for each x I have images.
Oh yeah, yeah.
I
Okay, if
contain
you
the
also
both.
fix an x, yes.
Yeah, okay.
Okay, we
Shouldn't they-
denote
Shouldn't they start from the same point?
the what?
Shouldn't they start from the same point, f and g, and continue?
No, they don't have to. But I'm sure you're. I think you have some idea what it is, and Yeah, we will get there. And we denote this by like this. So it's not an equality sign, and maybe it's how we are going to weaken this notion of equality. And for notation purposes, sometimes we write h of t. So when I fix a t, this is a function from x to y. And if you don't want to write the argument, like x is not doing it, has no purpose here. So sometimes we write things like, okay, h of 0 is f, h of 1 is g, so you don't have to write the argument x. Okay? Yes?
H is continuous, right?
Yes. From now on, everything is continuous. Yeah. It is continuous in x and also in time, in t. Okay. So, let me make it plain. Let's do an example. Let x be any space. And let's take two maps, f and g, from x to Rn. You can pick your favorite Rn. And I claim that they are homotopic to each other. So consider h, x times Ri to Rn, such that h xt is f of x 1 minus t plus g of x times t. You can easily check, I think you can check that if these are continuous functions, this is also continuous. So this, you can see that h x 0, what do I get? If I plug in 0, I get f of x. h x1 is g of x. So f and g are homotopic. Any questions on this? So every map, all maps into Rn are homotopic to each other. This is not a very special case to Rn. The reason, if I take any convex subset of Rn, this would still work. What I want is, okay, if you think about what this is doing, it is, if this is f of x, and this is g of x, for some fixed x, okay, let's say this is f of x, and this is g of x. This equation is literally the line segment from this point to this point, or yeah, from this point to this point. Yeah. So long as your subset is convex, meaning these 2 points are contained in my space, this function will be well defined, and I'm black boxing the fact that it's continuous, but it's not very hard to see, and we have the homotopy. Questions?
With
Concerns?
Euclidean topology, right?
Hmm?
With Euclidean topology, right?
With Euclidean.
I mean, this is continuous with Euclidean topology.
Yes, but what about x? Well, but yeah, with these, with respect to these, yeah, Euclidean continuity. Okay. Okay, so this is called, this is, you're gonna see this homotopy in this area many times. So we gave a name for it. This is called the straight line homotopy. Straight line homotopy. It is a peculiar kind of homotopy. It doesn't exist all the time. So for example, if I take the punctured plane, and if I take this arc, let's call it F, and if I take this arc, let's call it, G. Well, now I can't use straight line homotopy because if you think about this point, the straight line homotopy would give you a path like this, but this point is not in my space, so this doesn't work. But this doesn't mean they are not homotopic; they are still homotopic to each other. What I can do is I can slowly rotate F into G, right? It needs to be a movie, okay? You can't just, so you have to visualize the movie and then mathematically write what that would mean. So maybe at time 0, it's like this. And, okay, let me try to, I'm very bad at drawing things. So this was G. Maybe this is like time one half. And at time 1, they're on top of each other. Yes.
Can you explain the effect of the choice of directness for the arcs?
Okay, good question. Why do I give an arrow? Why would I put an arrow like this? In my head, this is a function. Okay, in my head, f is a function from the interval to the punctured plane. Yeah. And as it goes from, so this is 0, this is the starting point. So this is f0 and this is f1, and it goes like this. So like if we try to parameterize f, what would be right? What would we write? Let's see. I think it has to do with cosine pi x, comma sine pi x. I hope. Right now, okay. This arrow means in my head. Okay, it starts from here and ends here.
And so if we make F stay that way and G go the other way,
They would
should
still
just be a matter of reversing time.
Yeah, I can come here. Well, what I can do is, I can do it. I can reverse it, right? So what would I have to do is I would take this, and I would have to put, okay, wait, maybe I can't. No, I feel like I can, but yeah. I think yeah, it's because there's no problem with cutting itself, so I can just cut itself and like turn it around somehow. Okay, good question. I didn't think about this, but yeah, we can think about it. Okay, let's write to homotopy since we have this. Okay. I believe what we are doing is we are changing the starting point of this function. So I think what we need to do. Okay, let's see, cosine pi x plus t times pi. Okay, let's do this. And sine pi x plus, is this working? Okay, I think this is working. This makes sense to me. It's like, okay, when t is 0, it is f. And as t goes from 0 to 1, it is changing the starting point of this path. I think this is working. Okay, questions? So they are homotopic. Yes?
I think if the direction of F will be reversed, maybe they can't be them.
You think they can't be homotopic?
Yeah.
I feel like they can. Let's think about this. It's a good question. I feel like they can, but maybe they can't. Maybe they're not homotopic. Okay, so now, okay, we are getting comfortable with homotopies. I think it's a good time to define the homotopy equivalence. we say that x and y are homotopy equivalent, if so it is very similar to the definition of homeomorphism. There exists f x to y and g y to x such that f composed with g is now we don't want it to be equal but homotopic to identity of y, and this we want this to be homotopic to the identity of x. Questions about the definition? Okay. One example. Okay, let's do an example. So let's try to come up with two spaces that are not homeomorphic to each other but homotopy equivalent to each other. Let y be a convex subset of Rn. Then I claim that y, and when this happens, we can denote, let's choose to denote it like this, okay? I claim that y is homotopic to a set with one element. Okay, so you can put anything inside, I put star. Let's try to see if this is true. So we need to come up, like if you look at the definition, we need to come up with f and g, and somehow we need to find a homotopy between the compositions and the identity. Well, we have a very easy set, so it won't be very hard to come up with the maps. Let's say f is from this set to y. All you need to do is choose a point in y. Let's say f of star is some p in y. And we need to come up with a map from y to the point. Well, there's only one map. So this is star. Okay, so let's try to see what happens when we compose them. If I do this, what do I get? So, okay. Is f of star. So g of y is star, and f star is p. And the other composition is, okay, f of x, okay, I can't put x, I need to put star. So f of star is p, and this is star.
What was the definition of convex subset?
Convex means if you have 2 points in the set, every point in between is also in your set. Okay, we are so lucky because if you see, this composition is identity. Okay? So because there's only 1 point, so this g of f is a map from star to star. Well, it is the identity map. So this is ID star already. So we don't need to do anything about this. But for this, well, this is not the identity map. It's actually very bad. It's very far away from being the identity map because it's the constant map. So this is a map from y to y, and it's the constant map. I'm going to show it like this. It's the constant map, sending everything to p. Okay, let's try to homotope this. Let's try to come up with a homotopy. Well, it's going to be the straight line homotopy. Okay? So 1 minus t times constant p plus t times x. So at time 0, it is the constant map p, sending everything to p. And as time progresses, it turns into the identity map. So this, oops, no, this shows that this is ID y. So they're homotopy equivalent to each other. Any questions about this example? Yes.
I'm wondering if you have a good intuition for like how we sort of get both sides of like an equivalence relation, given that we've kind of defined the homotopy with like a clear distinction between like like the starting and ending, like how, for example, if we wanted to make a homotopy map,
Yeah.
starting from a, you know, say like we have maps that are definitely not injective, but we want to kind of come up with like the reverse direction of the homotopy, starting with say like a point and kind of expanding it out into like a larger thing.
Yeah.
What's the intuition for making some kind of continuous map that somehow encodes enough information in this that we can actually put it out?
If I understand your question correctly, the way I think about it is the other. Okay, first of all, okay, let me make this remark. If I have a homotopy, if this is a homotopy, then this is also a homotopy. So it's like reversing the video. You go back in time, right? So the way I think about this, for example, instead of starting the point and expanding, it's more intuitive for me to start from the larger thing and get smaller. Maybe this makes sense. So like in this case, what's happening? I have a convex set, and what this is doing? Well, okay, this point need not be. Okay, let's pick P. Maybe P is at the center to see it easier. So what is happening is I'm sending every point to the center in time. So it gets smaller and smaller, the image, and then it becomes. Does that answer your question?
Yeah, I guess it seems like this works because we're still like our domain space and like the range aren't going to be switching, and so like since the domain space has enough information to be able to admit a function that will send it to the larger space, then like as long as it's possible to get there, you can run it in both ways, like we talked about.
Yeah, in this case, the domain space is y, right, for this function. And yeah, we do have information about y. Yes,
What is it that you call star?
it's just that whatever you want. Just whatever element you want.
An arbitrary element.
Yeah, you can write 5 if you want.
And can you remind me the convex set?
Yes, okay, let me write it the definition. Okay, I'm gonna say if P and Q are in Y, then intuitively this means every point between P and Q are in Y, but mathematically speaking it means PT plus 1 minus T Q is in Y for all T, in 0, 1. And this is the equation of the line segment from Q to P. And this is exactly what we want, so it's very convenient
But
for us.
that's a straight line, right?
Yeah, it's a straight line. Yeah, it's a convex subset of Rn. Otherwise, yeah, what do I mean by in between?
In that case, for example, star topology would be non-convex.
Star
Like,
topology.
imagine a set like star.
A star shaped?
Yes,
Yeah,
star shaped.
yeah, okay. You can, yeah, we can make this even better. If you have a star shaped space, then you can still use this, you can still deform it to a point, to the star center.
Okay.
This is very special case of being a star shaped surface. Does that answer your question?
Yes.
Okay. Well, this is very. Okay. This is a very special case, so we chose to give some names to these situations. So I want to write those so you have some familiarity with this. Like I want you to remember some words when you're out of this talk. So. If we have a map from X to Y, and suppose F is homotopic to the constant, let's call it Q, to the constant map for some Q in Y. If this happens, we say F is null homotopic. It's just a fancy name to mean, well, it's homotopic to the constant map. And we say that X is contractible if identity of X is homotopic to the constant map. So this is what happened in this case. So we show that any convex subset of Y of Rn is contractible. So you can contract it to a point in time. Okay. What do I say next? Okay, maybe if you're thinking about a non-contractible space, okay, it's very hard. I mean, we can't really show that it's not contractible, but I'll try to give you an idea. For our fundamental example for a non-contractible space will be S1. Okay, so there's nothing here. This is not a part of my space. If this was a part of my space, I can contract S1 to P, like slowly deforming it like this. And I'm not even moving P. But this is not a part of my space, so I can't do that. Maybe this is not S1 but D1, D2. Okay, I'll try to convince you that this is not contractible. So if there was a homotopy, so suppose we have a homotopy to the constant map P. Okay, what needs to happen is, and suppose throughout this homotopy, P is not moving, right? And then the points that are close to P should behave like P, okay? So this is about continuity. But like, if I have a point here, this is going to slide down to P, and then this is going to slide down to P. So these are the paths that the points are going to follow, okay? If you go all the way around, well then, because of continuity, they all have to follow this path. You might say, well, maybe this point is going to follow this path. Well, no, because if you follow this path, but this point follows this path, it won't be continuous, okay? So then you go all the way around, and all of them follow this path, and then once you come here, you realize that, well, okay, this point that is very close to P is following this giant path, whereas P is just sitting there still. So this is not a continuous. This won't be continuous. So that's why this won't happen. This is just an intuition. To prove this, we need more machinery. So I'm not going to do that now. But I hope if you think about it, you can see that you can't deform S1 without breaking it. But if you break it, if you remove a point, you can deform it to the point. Okay. Questions? Okay. You can show that homotopy equivalence is an equivalence relation. So if two spaces, well, if X is homotopy equivalent to Y and Y is homotopy equivalent to Z, and X is going to be homotopy equivalent to Z, you can show all these results. And I want to mention something that is happening here. So this is a very special case, okay? Actually, this is the homotopy equivalence we use a lot when one of the composition is exactly the identity map, okay? We have a special name for it. So let me define it so you have a feeling for it. Okay, now, suppose we have a subspace of X, and we say that X deformation retracts onto A. Okay, let's see. So we need to we have the inclusion map. And what we want a homotopy. We want a homotopy such that the first one is going to be identity of X. The last one, the last one will be just A. Okay, the last one will, if you okay, let me put it this way. How do I want to write this? The last one restricted to A is identity of A. And, well, okay, do I want to say it this way? Okay, I'm going to say it the other way. The last one, let's call it R, and R is going to have a special property. And this is, some sources include this, but I'm going to write it. So the homotopy is constant on A, it's not moving. And what is special about this map? So if I go from, okay, this is a map from X to A, and this is identity of A. So, alright, I know this looks like a lot of words, but let me try to explain what's happening here. So, suppose you have the annulus. This is where it's filled. And I have a subspace, A. So I want to come up with a homotopy that is fixed on A, okay, that does not move A at all. And I want to deform it towards A. So I think you can visualize this. So let's try to write it. Or show it. So in time, this is going to be thinner. And thinner, and eventually it will be just A. Okay, any questions about this? Or Another example is if you have the cylinder, and maybe this is your subspace, the bottom, and you can push it down, deformation retract onto the bottom. And maybe let's try to write down the map for this. So what is a cylinder? It's S1 times I. And I want to write a map from S1 times I to S1 times I. Okay, let's try this. So this gives me my height in the cylinder. So, and I don't want to change its location on the circle. So I want to keep this the same, and I want to change its height, starting from itself and ending at 0. So if I just write T, if I just write this, I'm done. Nice. Yes.
Do we ever need to think about how the embedding I is playing into the scenario? Because it seems like we're mostly thinking about the map that corresponds to the homotopy.
This is not an embedding. This is the inclusion. So it's the set. You can think. So what it's doing is I of A is A in X.
Oh, okay.
So it's not doing something funny. It is literally the inclusion map. Okay, let's check. If S is 0, okay, observe that for all T, so the homotopy is not doing anything on this subspace. It's keeping it fixed for all times. And at time 0, I'm identity. And at time 1, I'm on the bottom circle. So this is a homotopy coordinates. Any questions? Yes.
Is a homotopy map always in such a form that we like take a product with a new set I,
Yes.
which will behave like time dimension?
Yes, always. That's how we define it. This is a homotopy is always a family of maps that differ continuously. Any other questions? All right. Okay. In the last 5 minutes, I think I can define the fundamental group, maybe. Okay, I'll try to make this quick, but okay, lots of definitions. Okay, first of all, if I have a map from the interval to X, it's called a path. On X? Well, because if you look at the image on X, it actually looks like a path. Okay. And if the starting point and the end point are the same, then F is called a loop. So if this is my space X, maybe this is a path, F, and, well, this is a loop at this point, something like this. Okay. Now I want to Well, paths, these two paths are homotopic to each other, as we saw before, but I want to capture, somehow, I want my definition to capture this puncture. Okay, somehow I want to come up with a way in a way that I can detect this. And for this, what I'm going to do is, I'm going to force my homotopy to have the property that this endpoints are fixed throughout the homotopy. If you think about it, if these endpoints are fixed, I can't deform this path to this path. So my homotopy will detect this puncture. Because if I don't puncture this, I can just deform it. So let's define it. Let's say gamma 1 or gamma 0, gamma 1 from I to x are two paths such that their starting point and end points are the same. So from P to Q. Then we say that they are path homotopic. So what I want, there exists a homotopy from I times I to x such that, okay, the first argument is the argument of the path. So I want this to be one of my paths, and I want at time 1, I want this to be my other path, but let's see. But I also want, if I'm on the end point, so this, or the starting point, for at all times it is P, and this is at all times Q. So if this is gamma 0, and maybe this is gamma 1, a path homotopy looks like this. Okay, it's a movie, and the starting points and end points are fixed. Okay, any question about that? Yes, good question. This is stronger. If two paths are path homotopic, they are definitely homotopic. Because for homotopy, I don't have this one, this part. And this is the same. This is a homotopy from gamma 0 to gamma 1. But now I also require these two conditions. Okay. So now if I can do this with paths, since loops are paths, which are somewhat special, I can also define it on loops. Definition. Okay, let's fix a point. And I'm going to define pi 1 x naught, which is called the fundamental group of x. It's a very important object. This is a set of all loops at x0, but I have an equivalence relation on it. I say gamma 0, I'll say gamma 1 and gamma 2 are equivalent if gamma 1 is path homotopic to gamma 2. So in words, the set of all equivalence, this is an equivalence relation, path homotopy. And path homotopy, the set of all equivalence relations under path homotopy for loops at x0 is called the fundamental group of x at x0 or something. And this is this is actually a group, which is a crazy observation. but for now it's just a set. I think you can show, you should, with what we have done, you can show that if a space deformation retracts onto a point, then you can show that it's this consists of a single point, which is the constant line. Unfortunately, it takes some more machinery and some more work to compute some the fundamental group of some other spaces like S1. And we need to show that this is a group, what is the group operation, etc. But I hope this was a good introduction to the story, and it's a very rich subject. Well, yeah, I hope you enjoyed it. Any questions? Right. Yeah.
So, is this fundamental group is like is it an equivalence class?
It's the set of equivalence classes.
Okay, and an equivalence class would be path homotopic loops, set of path homotopic loops.
Yeah, one class consists of loops that are all path homotopic to each other. Yeah. Any other questions? Yes.
From the previous example, you erased that if we reverse the order F, remember?
Oh yeah.
So maybe from there you can say there.
Like the question you asked earlier, like this one. This one. Okay, so you're asking about this, right? Well, they're definitely not path homotopic, regardless of what you do, because this is punctured. Okay, but if I don't fix the endpoints, okay, let's try to see.
I think you can just kind of slither it around.
Okay, like a snake?
Yeah.
Yeah. Okay, if this is the bottom, I can just go like this. Okay. Thank you all for listening. Then. Sorry. That's bad habits.
Berke. Hey. You hi. Doğa. Maçı da şeydi. Selam ver selam. Arkadaşlar kameraman bendim.